Welcome to Introduction to Business Statistics. For all of you math enthusiasts out there that enjoy theorems and proofs, this might not be the class for you. In this course, we intend to take complex statistical concepts and break them down into layman's terms. In short, we hope to help you understand the statistics that you see around you every single day and how we use statistics in order to make very important business decisions. Statistics is the art and science of collecting, analyzing, presenting, and interpreting data. We often hear on the news about the average amount that a consumer will spend this holiday season. We also hear about the average amount that a consumer should expect to pay at the pump. Averages are numerical measures that attempt to summarize the central tendency of data. We live in a poll-driven society. We often hear journalists on the news use polls in order to summarize how we feel about different issues. As an American citizen and registered voter, have you ever wondered how journalists can accurately predict how Americans intend to vote in an upcoming election even though they've never spoken directly to you on the phone? Later in this course, we will discover how statistics allows us to analyze a small sample from the population and accurately predict what the entire population feels. How many of you have actually turned to Consumer Reports before making major purchasing decisions? Consumer Reports collects samples of products and evaluate those samples in order to determine the performance level of these products. They then compare the actual performance levels to the company's claims of how the products are supposed to perform. Before we dive deep into statistics, let's review some basic vocabulary terms. Data. Data are the facts and figures that are collected, summarized, analyzed, and interpreted. Data can be classified as qualitative or quantitative data. Many more statistical analysis techniques are possible for quantitative data opposed to qualitative data. Qualitative data are labels or names that are used to identify an attribute of each element. Qualitative data may be numeric or non-numeric. The statistical analysis for qualitative data are very limited. If you encounter data that is non-numeric, then that data is definitely qualitative data. However, if you encounter numeric data, then that data may be qualitative or quantitative. Quantitative data indicate how much or how many. Quantitative data are always numeric. Arithmetic operations and analysis are only meaningful with quantitative data. If you encounter data which are numeric, you should ask yourself two questions. First, does this data indicate how much or how many? And second, would arithmetic operations or analysis on this data be meaningful? If the answer to either of these questions is yes, then this data is quantitative data. Let's review the variables listed on this slide, and for each variable determine whether this is qualitative or quantitative data. You should pause the video at this time in order to complete this exercise. Social Security numbers are qualitative data. These are simply labels that are used to identify citizens in the United States. A birth date with the day and the month, such as March 23rd, since this contains non-numeric characters, this is definitely qualitative. A birth year is quantitative. A birth year is useful in order to determine how many years a person has been alive. Arithmetic operations on birth years, such as computing the sum or the average, would produce meaningful results. A zip code is qualitative. A zip code merely indicates a person's location. A name is qualitative. Names are non-numeric, therefore they're definitely qualitative. A GPA is quantitative. If we performed arithmetic operations on GPA data, such as computing the average or sum of GPA data, this would produce useful results. And last, the weight is quantitative. Arithmetic operations would also be meaningful on weight data. Elements. Elements are entities on which data are collected. A variable is a characteristic of interest for all elements. The set of measurements collected for a particular element is called an observation. For example, suppose we were interested in doing some research to analyze the fuel efficiency of a mid-size SUV. We are asked to collect the model and average miles per gallon for each SUV in our study. For this study, each SUV would be an element for our study. We would have two variables that we are collecting for the study. One is the model of the mid-size SUV, and the second is the miles per gallon for each of the elements that we collect. For this example, one observation would contain the model and the miles per gallon for that element. A qualitative variable is a variable with qualitative data. A quantitative variable is a variable with quantitative data. In the previous example, model would be considered a qualitative variable. Since the model of a vehicle contains non-numeric characters, for each element, the model would be considered a qualitative variable. Miles per gallon, on the other hand, would be considered a quantitative variable. Populations and samples. It is very important to understand the difference between these two terms. The population is the set of all elements of interest in a particular study. A sample is a subset of a population. Most studies that are reported are based upon the analysis of sample data that was drawn from the original population. Here's an example. Suppose we are interested in doing a poll to determine the forerunner in an upcoming governor's election in North Carolina. For this study, the population would be every single registered voter in the state of North Carolina. We could randomly select 200 registered voters in North Carolina, poll those 200 voters, and collect data from them. In that example, the sample of 200 registered voters selected from North Carolina would be considered our sample. Our course will be divided into two major sections. The first section will deal with different descriptive statistics measures, and the second part will address different statistical inference techniques. Descriptive statistics is tabular, graphical, and numerical methods used to summarize data. In this example, the cost of tune-ups at Hudson Auto Repair was graphically summarized in the form of a histogram. If we state that the average tune-up cost is $79, the average is a descriptive statistic. Statistical inference is the process of using information obtained from analyzing a sample to make estimates about characteristics of the entire population. Most studies that we hear about are based upon statistical inference. In the studies, the researchers want to know something about a huge population. Instead of analyzing every element in the population, the researchers select a sample from the population. They analyze the sample and then make estimates about the entire population. Let's examine the Hudson Auto Repair example. For this example, we would start with the population of all past tune-ups performed at this auto repair shop. We would then randomly select 50 tune-ups from the population. We would analyze that sample of 50 and compute the average for our sample. We would then use the average from our sample in order to estimate the population average for all tune-ups performed at Hudson's Auto Repair. With statistical inference, the validity of the estimate for the population completely hinges upon the random sampling process in which the sample was selected from the population. Since we plan to use a sample in order to represent or estimate the entire population, that sample must be representative of the entire population. This random sample must be selected in a manner which is completely blind, and every element in the population has an equally likely chance of being selected for the sample without any bias. In essence, our random sampling process should simulate a procedure in which we place the name of every element in the population on a piece of paper and then put all pieces of paper into a huge bag. We then shake the bag up, put our hands over our eyes, and reach in and select items to be included in our sample. I often give the following example in class in order to illustrate to students the importance of random sampling. For my example, I tell students that I could very easily construct a study in order to prove the truth that women are much smarter than men. I tell students for my study I randomly sampled 1,000 men and 1,000 women and administered identical IQ tests. I explained that after analyzing the results of the IQ tests, women overwhelmingly outscored men on this exam, thus proving that women are indeed smarter than men. Instantly, students began to ask a lot of questions. Ultimately, their questions revealed that I went to an area with a very high dropout rate, high school dropout rate, and that's where I selected my random sample of 1,000 men. I then selected an area in a country that is nationally known for its great school systems. And those are the areas in which I selected my sample of 1,000 women. From this example, it was clear that my ultimate conclusions were completely biased. They were biased by my not so random process that I employed. From this example, it is clear that in order for statistical inference to work, an unbiased random sampling process is absolutely essential. We have prepared a series of 15 to 20-minute tutorials on a variety of statistical topics. Ultimately, our goal is to help you understand the statistics that you encounter daily and how these statistics are used to make very important business decisions. Ultimately, our goal is to help you understand the statistics that you encounter every day and how these statistics are used to make very important business decisions.